Hello everybody, today we are talking about Lesson 5, Interpreting Graphs. So in this lesson booklet, or in this lesson, we have a appearance of the data of the equilibrium process in sort of a graphical representation. So in our class, we actually did an experiment. We took the uh, we took carbonate, sodium carbonate, which breaks down to carbonic acid in a solution, and we reacted it with acid to allow for the formation of water and carbon dioxide. And then, because carbon dioxide is a gas, we actually collected data here where we took the sealed container. So it's my sealed container here, and we released the gas, dropping the pressure, and we notice this immediate spike. So this is us stressing the system, right? So that's stress. So that's what stress looks like in a graph. Here's what equilibrium looks like. Equilibrium will be a constant concentration, and then a stress will appear typically as an up and down vertical sort of change, although we also have seen some other stresses, and we'll talk about those in a second. And then the system recalibrates, and this is the shifting here. So that's shift. So notice that the stress is so fast that the system can't adjust fast enough. And then it will adjust backwards. So essentially we have decreased the amount of CO2 as our stress, and so then we get a shift, and that shift will respond in opposite to the stress. And in that shifting, we could also interpret that there would be a decrease in the amount of H2CO3 as it tries to compensate by creating more CO2 to compensate for the CO2 that we lost. CO2 was lost. Okay, so that's what we did in the lab. If you want to see more about that, we do have a video on our classroom stream. Now, let's look at some graphs. These are all the typical types of graphs, and I have done a classroom stream about these, but I want to kind of condense this down into a shorter version for those of you who've missed these days. So when you have a graph, the flat parts are equilibrium, and then the stresses and the shifts are the two separate parts. So I want to be able to identify the stress and identify the shift as depending on the different situations. So these graphs here are in terms of rate. And so looking at the rate, we know that at equilibrium, the rates should be equal. So that's why there's only one line on either side at the equilibrium. That's because the forward and reverse reactions are equal. And then the stresses, in this case, the addition of NO2 causes a sudden rapid increase in rate. But for one of the reactions, it'll be an increase in rate for the direction that you've added reactant for. So if you add NO2, NO2 is on this side, so you've suddenly given a big boost to the forward rate. Now, to compensate, the forward rate must slow down, and that's what this next part is. This part, the shifting, that's the slowdown as this excess NO2 gets used up and turned into N2O4. So after the immediate addition of the NO2, you have an immediate increase in speed of reaction, and then the shifting is back to the new equilibrium. Now you've added more particles, so overall there's an increase in the equilibrium rates. So that's where this little arrow is supposed to indicate, so that the equilibrium has shifted upwards. Opposite happens if you take something away. You get an immediate stress, and then which slows down that rate, whatever it is, very quickly. And then the rate has to climb back up from that position as the reactant in its reverse rate produces more NO2 to compensate. Okay, so overall, because you removed particles, the overall is going to be a decrease. So that's what these lines are here for. Now, if you wanted to think about this in terms of the kinetic energy distribution, this was our kinetic energy distribution, right? And this is our concentration percentage. We can think of it as the more concentration you have, the higher the graph is. So higher concentration is like this blue one, and that means there are more particles that are succeeding in the reaction. Lower concentration, less particles are succeeding at that reaction, no matter what the activation energy is of that reaction. So the forward and reverse reactions have different activation energy barriers. That doesn't matter. More matter, more quicker. Okay, so here we have the opposite case where we are affecting the concentration of the product. So if you add product, the reverse rate increases suddenly, and then it has to compensate and shift backwards. So we get that shift left. So we would say this is the stress here is added product, and then the shift this is showing a shift to the left. Okay, and we can see that little this little diagram here as well is helpful. And that's what I really want you to be able to do with looking at any of these graphs, no matter what they are. If I take the context away, can you figure out what's happening? So here is another stress. In this stress, we see that the backwards rate, the reverse rate, is decreasing suddenly. So that suggests that we are removing N2O4, and then the shift is going to be to the right now to compensate. And so that's what's happening here, and that's why this pink line is going upwards a little bit. So it's the little right line, that's the shift right. Okay, so that's rate of reaction. So now let's look at rate of reaction, but in terms of temperature and the effect of temperature. So when you add temperature, the reactions, notice that this is much narrower because temperature affects both forward and reverse rates, but it has a greater effect on the side that has an energy component. So in this case, the reverse reaction gets a greater boost because adding temperature actually gives it a benefit. It needs temperature to react backwards. So the reverse rate increases a little bit more, or quite a bit more in this case, than the reverse one. So here we have a stress of added T, and then the shift is now going to be to the left towards reactant, because we have this extra T and we need to use it up, and so we can use it up by converting to reactants again. If we decrease the temperature, we have the opposite effect. It is always the side with, let's see, is it always the side? No, not really. I was thinking it might be the side with the energy on it that's the most affected. Is that kind of what we're seeing? But no, I don't think that really applies. So let's just say that now we are decreasing the temperature, so we have to shift to compensate. So we're decreasing the temperature, so that means that there is a great change in the forward direction, and that creates I'm just going to erase these just because I'm a little worried about what these lines say. Yes, so the forward reaction, okay, I was right. All right, so the stress is here, the stress is temperature down, and then the shift is now going to be to the right, or product favored. So if you wanted to make this product, then you would really want to be doing this experiment at low temperatures. And notice again that because you are at a lower temperature, the new equilibrium, the low temperature equilibrium, is always lower in terms of rate. So lower rate overall, low T equals lower rates for both directions. And I believe I said increased temperature on the other side is overall increase rate. Now, one thing that's missing from this graph is a rate of reaction graph for pressure. So if you add pressure, it's like you are increasing concentration. So the forward reaction, the red one here, the forward reaction will be more affected because you are increasing the pressure on these NO2 particles, and you're decreasing the favorability of having more particles. And so there are more particles of NO2, so the change in volume has a greater effect on the left side, so it gets the greater boost in rate of reaction, and then over time it reaches a new equilibrium. Because you're at a higher pressure is going to have higher rate overall. Higher pressure equals higher equilibrium rates. So that's what's happening here. And you can see that, maybe I want to make a little colored version here. So there. And then if you can see here that we're going to get lower rates, lower pressure, lower equilibrium rates. Decrease the pressure, and again, it's going to be the left side that has the greater effect. So the left side is affected more strongly, and so it has to recover more over time. And so we will see that sort of slow climb back as its concentration values were more affected by the change in concentration. Okay. So let's look at the concentration versus time graphs. So I like these graphs a little bit more because I think they're more interesting, and I typically ask questions based on these graphs, not the rate graphs, just as a tip. So here again, we have the flat spots are in equilibrium. I'm going to maybe work this out so that I can kind of come back at it with my verse. So we have equilibrium concentrations here. And then we're injecting some extra NO2, just like we saw in the previous, but now because it's an equilibrium of concentrations, they don't have to end up at the same value. Because remember that from our equation here, we don't actually look for the same value. They're not supposed to equal 1. The ratio of them is supposed to equal k, and we don't know what k is in this case, but we could calculate it from the ratio of these two lines. So again, we have this equilibrium value here. And so because we are injecting extra matter, the values are going to go up a little bit from the original equilibrium. They're going to increase. Depending on the product or particle, we are going to have a greater increase or lower increase based on this equation here in terms of the overall concentration change. So we get this initial stress, right? And then we have the shift. And so that's the shift to the new equilibrium. In this case, it is a shift to the right, or shift towards product. So shift to product. And usually you can see the shift to product because the product has the upper moving curve. So the curve that moves upward, that's the one that's the shifting is towards. So let's look at NO2 here. We are removing NO2. So we see the stress here of the removal, sudden decrease in concentration, and then the shift will be an opposite. So in order to shift opposite to a decrease in concentration of NO2, we need to shift left or shift towards reactant. So that means that the reactant will see the increasing curve, and the product will see the decreasing curve. So that's where those shifts are coming in. I'm going to get rid of these lines. I don't like them very much. But I do like the idea of the shift there. Overall, you've lost molecules, so you have an overall decrease in equilibrium. Okay, so let's look at this next one. Here we have N2O4. We have the stress is that we are adding N2O4, and so we get this sudden increase in N2O4, and then we get the opposite shifting. We get that shift away from N2O4. We get a shift to the left towards reactants, and that's why we are seeing this upper curve on the reactant side, not on the product side. Reduce the amount of N2O4 on this next one, and you get a sudden decrease in concentration and then a shift, and as the shift happens, you get a opposite direction with the shift, so the curve for the N2O4 is in the opposite direction, which tells you that the shift is towards products. Product, or shift to the right. Okay, so if the curve goes like this is a shift towards this side, right? And if you have a curve that goes this way, then this is a shift away, right? So whatever it is. So if it's reactants, it's a shift towards reactants. If it's products, it's a shift towards products, etc. A change in concentration will affect both reactants and products similarly. Adding matter, I guess, which is what I'm trying to say here. Adding matter. Whoa, doesn't like that. Let me just use my pen here. Adding matter increases both equilibrium concentrations. Removing decreases both. So adding matter, higher reaction rates, higher concentrations at equilibrium, no matter what. All right, so now if you have temperature has a little bit of a difference. This is one of the ways you can tell it's a temperature curve, is that temperature has a gradual effect on both concentrations. It has an instantaneous effect on the rate of one of the reactions, but it has a gradual effect on the actual concentrations themselves. So we typically see this kind of curving, where there's not a strong spike, no vertical line or vertical spike in the curve. It's instead just a smooth curve. And this can be the trickiest one to figure out because it depends on you knowing if it's exothermic or endothermic, or you can interpret whether it's endothermic or exothermic. So here we see that NO2 is increasing under increased temperature. That means that NO2 is the side that's using the energy. So this curve here tells you that this is the direction. So let's go like this. This must be the direction that uses energy. So think about that as a possible question type that we could do. Is I could give you a blank graph, or the graph with just the curves on it, and then ask you like, so based on this graph, do you think that this is an exothermic or an endothermic reaction? And that could be a little bit tricky to figure out, but I believe that you could figure it out if you had to. Now, looking over here, we have the decrease. In the decrease case, we see that if one side goes down under a decrease, that must be the side that uses energy. Must be direction that uses energy, or endothermic. So the endothermic direction under a decrease in temperature will be the one that goes down. Under an increase in temperature, the endothermic direction will be the one that goes up. Okay. Now there's the last two graphs that I want to show you are the pressure graphs. So if you have a pressure graph, then you will, my typing this afternoon was not great. Pressure So if under pressure, what we'll notice is a distinctive double increase. So notice that double increase. So that's specific to pressure. So pressure will always have this increase where you see all of the products and all the reactants increase. and that's the sign that you've changed the pressure. That's because pressure affects all reactants and products. In some cases, it will have very minimal effect. In some cases, it will have um, an important effect. So in some cases, it won't have, the products and reactants will be affected equally. But in this case, because we do have a difference in the number of particles on the left and the right, the one side is going to have a greater increase. So this side should be the greater increase, more affected. And so because it's more affected, then we have to compensate for the new concentration, the larger increase in concentration of the NO2, which causes the N2O4 to have to compensate. And so the N2O4, so the extra NO2 has to be used up and shifting the reaction to the right. So we can say that this is a stress is increased pressure, and the shift is going to be towards product. And again, you can find that towards product right here from the upper curve. On the other side, we see the upper curve down here. So that means that we are shifting towards reactant. Shift towards reactant. Or to the reactant to the left. And that's because we've decreased. But we see the double decrease. So that's the double decrease. So double decrease. And that's because of its pressure. Okay, so we could kind of summarize. Maybe we can summarize with the possible types we have. We have something that looks like this. So I'm just going to do I'll just do the 3. So we're just going to focus on concentration, 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 and we'll just we'll just get 2 lines here. Just 1 second. 1, 2, copy, paste. Okay. I'm going to put a big R here and a P for products, reactants, products, reactants, products. So the 3 shapes that you can possibly look for is something like this. That. You could look for something that, and so this, I'll start name this one. So this is increase in a concentration. And by the same token, we could do the decrease in the concentration, which would be the opposite. This is going to be a change in temperature. And so the change in temperature could look like this maybe, right? And then the last one is going to be the change in pressure. And the change in pressure has the distinctive double increase. So we want to think about these double increases, and then we'll say maybe something like that. So that's the 3 different types of curves. So notice the difference. We have the double spike in the pressure. We have no spikes in the temperature, and there's a single spike in the concentration one. Much harder to figure out from the rate of reaction. Also very difficult to measure. So that's why it's not nearly as useful. So that's the basic ones. There's some extensions here. If I told you that it was exothermic or endothermic, then I could ask you, what does this graph mean in the middle here? So, we could say something like, if exo, then this is, so if it's an exothermic reaction, that's a reaction that produces energy. So the energy is on the product side. So that means that this must be a decrease in temperature. No, an increase in temperature because we are producing extra reactant. So then this is an increase in temperature. So that's a kind of question we could ask. I could also ask if this was an endothermic reaction, have we increased or decreased the temperature? So, um, so I guess maybe I'll organize this a little bit nicer. And I'll write out the question. If exothermic, is this an increase or decrease? Oh, okay. In T. So something like that. Maybe I will convert this to text, just text so we can see it. Is this an increase or decrease in T? And then we'll call this answer. Oops, not an emoji. So there's our answer. I really wish it would just do the thing I want it to do when I want it to do it, right? Okay, so that's kind of the question. We can do other things like that, but the other ones are pretty straightforward. Okay, we did this question in class. We said here is a chemical reaction that's endothermic. And so if I drew out this graphic on the left, then we could ask you what happened. And we can see the stress on the left here is that the acetic acid, CH3COOH, was increased. This reduced both reactants had to reduce in response. And there was a slight increase in product, which means that the direction of shifting is towards the right. On the other side, we have a temperature change because there's no spikes in it. And the reactants are increasing. So that means that we are shifting towards the side that has energy on it. So we must be shifting towards the left. And that would indicate that the temperature has gone down. So we're getting less product. So that's the kind of questions we're going to do, and there's going to be a worksheet that has that you can do as well. All right, thank you for your attention, and have yourselves a great day.